Hello, I just wanted to work on some of these optimization problems that we started together. And so we have this problem here. A rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are to be 1.5 inches, and the margins on the left and right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So if you remember when we were talking about these the other day, we said that we would identify all given quantities and the quantities that are to be determined. So some of the quantities that we know are that it's got to have 24 square inches of print. We know that the top and bottom margins have to be 1/2 inch and the left and margins have to be 1 inch. And then we are asked to find what are the dimensions so that the least amount of paper is used. All right, so first, after that, we said, well, let's draw a picture and see if we can figure out what's going on. So we've got a rectangular piece of paper right here, page of print, and it has to contain 24 square inches of print, but we know that at the top and bottom we have to leave a margin of 1.5 inches and on the side 1 inch. So I'm going to try and draw this so that it's a little bit more at the bottom and the top and a little bit less excess space on the sides. All right, so we would say that this dimension right here is 1.5 inches, and same thing here, this is 1.5. And then on the sides, this is going to be 1, and this is going to be 1. And this right here is where the print is going to be. Think about a book where you've got the margins around the edge, and so this is where the print is going to be, and this has to be the 24 square inches. All right, that spot in the middle. Okay, so then we need to come up with a couple different equations. Remember we talked about the primary equation, and that was what we were trying to minimize or maximize. All right, and so it's asking us what should the dimensions of the page be so that we use the least amount of paper. All right, so this right here is the page that we're talking about. Right, so they're asking what are the dimensions of the page so that we use the least amount of paper. All right, so and again, it would be like, what is this right here? What is this right here? All right, and the way we're going to do this, because we also want to talk about this region right here, we're going to call this right here X. So this measurement from the top of the printed part to the bottom printed part. And then we've got this 1.5 and 1.5, and then we'll call this part Y. And the reason for doing that would just be simply because now we're going to add amounts on, and so we would say that this whole side right here is going to be X plus 3, the 1.5 from the bottom and the 1.5 at the top, and we'll say that this whole thing right here is going to be Y plus 2. Again, the advantage to that would just be that we're less likely to make mistakes when we add things on than when we subtract. So instead of calling this X and this Y, the whole thing X and the whole thing Y, we'll call it X plus 3 and Y plus 2. All right, and so we'll say that the area of this whole page, right, that we're trying to minimize, again, that's because of the least, the area of that is going to be X plus 3 times Y plus 2. Right, again, you could do this a different way where you call this X and then later we're going to end up with a different equation for our secondary. So right now here we will say that this is the primary because it is what we were trying to minimize. And again, we know it's minimized because it says least. All right, we already know that the area of this is 24. And so we're going to say that the printed area is going to be area equals, right? So the printed area is going to be X times Y, and we will end up with, since we know that is 24, we're going to say 24 equals X times Y. Again, this is really a huge benefit to us calling this X and this Y. It's going to make it much easier for us to solve for one of the variables and replace it in here. If we had done x minus 3 and y minus 2, it would be very difficult to solve for one of the variables. So again, another really strong argument for us using this as x instead of this as x. Okay, so if you remember then, after we came up with our primary equation that was in terms of maybe more than one variable, and in this case it is, then we would come up with a secondary equation, which is this, right here, right, 24xy, and we're going to use that equation to replace one of the variables, either x or y, with an expression in terms of the other one. So I'm just going to randomly choose one, and we would end up with, if we solve for y, we would end up with y equals 24 over x. All right, again, you could choose to solve for x and get x equals 24 over y, but we're going to go with that. Okay, so again, our job is to get the primary in terms of a single variable, and so we're going to take and we're going to write a equals x plus 3, but when we get to y, we're going to replace it with 24 over x. All right, so we have our primary rewritten, but now in terms of a single variable. All right, let's multiply this out. So we've got x times 24 over x, which is just going to give us 24. Then we get plus 2x, and then we get 3 over 1, or 3 times 24x, which is going to give, 24 over x, which is going to give us 72 over x, and then we get plus 6. Right, so area is now equal to this. Let's combine like terms. And so we get area equals 30 plus 2x plus 72 over x. Okay, this is the spot where we have to talk about the feasible domain. And again, if this were not a word problem, we would just say that the domain of this was just all real numbers except x equals 0. But we know that it doesn't make sense, because this x is representing a length, it doesn't make sense to put in any negative values either. Right, so we definitely cannot use 0. We definitely cannot use negative numbers. And then the question would be, is there a maximum? So at least we want to say that x has to be greater than 0. As we keep, this is going to get a little bit weird here, so just try to hang out here. As we increase the value for x, right? Since this is a fixed area, each time we increase x, what that means is that we will decrease y. So think about this back up in this area that we're talking about. That x times y is 24. We know we can't have x equals 0. We know we can't have it be negative. But really, there's no reason why we couldn't say x is 100. All right, so let me just kind of write that down here. If x is 100, then y would be 24 over 100. And we would still get 24. It would be weird to have a page that was 100, where the print was 100 inches tall, and the width of the print was 24 hundredths, but mathematically there's no reason why we couldn't do that. Again, I think it would be really hard because you would just end up with like single letter. As we get this y value smaller, it would be so super skinny like this that we could probably just fit a single letter in there. It'd be very difficult to read. But mathematically, there's no reason why we can't do that. So what we're just going to say is the domain is x has to be greater than 0, but there is no upper bound from a mathematical perspective. And so then we would just say that's our feasible domain, right? If you remember one of the other problems that we did, we had a bounded region, which was really nice because we could use the extreme value theorem. But in this case, we don't have a bounded region, so we're going to see what happens when our region is unbounded. All right, so then after that, we're going to take the derivative of a. So dA dx, again, I'm saying I'm going to take the derivative, and because the function is in terms of x, it's the derivative of the area function with respect to x, which is our variable. All right, so when we take the derivative of this, 30, taking the derivative of that just gives us 0. When we take the derivative of 2x, we get 2. And then when we take the derivative of this, let's remember that this is the same thing as 72x to the negative first. And so we would end up with negative 72x to the negative second, which is the same thing as dA dx equals 2 minus 72 over x squared. Right, and now we're trying to find where are the max and min values, because again, we're trying to find the least values. We're looking for a minimum, right? So we've taken the derivative. This is the spot where we're looking for critical numbers. And so we would say, okay, well, let's set this equal to 0. So then if I move this term over to the other side, I'm going to again end up with 2 equals 72 over x squared. And then I'm going to multiply both sides by x squared. And so I end up with 2x squared equals 72. I'm going to divide both sides by 2, so I get x squared equals 36. And then again, without a context, we would say x equals plus or minus 6 here. But because we have a context and we know that we cannot let x be less than 0, it has to be greater than 0, then x equals 6 is the only solution that makes sense. Okay, so then again, because we have an unbounded region here, what we have to do is we have to make sure that we use the first derivative test instead. And so we're going to set up intervals. So I'm going to just write that domain is unbounded. And it's not even closed on the left here. So we're just going to say domain is unbounded on the right. So use first derivative test. All right, so we need to set up our intervals. We need to say what's our test value. We need to say what's the sign of f prime, and then our conclusion. All right, so here our interval, since that's our only critical number, it's just going to be the lowest x value, which is 0. So 0 has to be less than x, has to be less than 6. Again, feel free to use this notation, 0 to 6. And then we're also going to say 6 to infinity. All right, so we could write that again as 6 to infinity. All right, so test value or test point, I'm going to just choose x equals 1 for this. And in here, let's just choose x equals 7. All right, and then the sign of f prime. So again, here we are. We can use this right here, which is what we got. So if I plug in 1 here, I'm going to get 2 minus 72, which is definitely going to be negative. And then if I plug in 7, 7 squared would be 49. 72 over 49 is not 2 because, all right, let me write this down. 72 over 49. In order for it to be 2 or bigger, to get this to be 0 or negative, this would have to be greater than 98, right? Because 98 is twice 49. So this is a fraction that is between 1 and 2. So when I do 2 minus something that's between 1 and 2, I'm going to get a positive number. So here f prime of 7 is greater than 0, right? So here we would say, well, this is decreasing and this is increasing, right? And so again, if you remember when we went from decreasing to increasing, our conclusion is that value, 6 right there, is a minimum, right? So then we would say x equals 6 minimizes the function a. All right, and again, a is a function of x, so we can say x equals 6 minimizes a of x. All right, so then we have to use the secondary equation. So let me get rid of this here. Use secondary equation to find y. All right, so again, our secondary equation was this, 24 equals x times y, or we could even go so far as to use this, and we say we know that x is 6, so we've got y equals 24, whoops, you can't see that, y equals 24 over 6, or 4. Okay. All right. So then we have to go back and we have to make sure we answer the question. What should the dimensions of the page be? And again, this is not the page. This is not the page. That's just the print region. And so we need to find this amount right here. So we know that x is 6 and y is 4. Again, sorry, you probably can't see that. X is 6 and y is 4. But if you look back at the top of the page, to find the whole area of the page, we have to do x plus 3. So 9 inches. And here we had to do y plus 2, so this should be 6 inches. So we would say the dimensions of page are 9 inches tall and 6 inches wide. Okay. Hopefully you feel all right about that. All right, let's take a look at the next example. Okay, so in example 4 here, we've got 2 posts. One is 12 feet high and the other is 28 feet high, and they stand 30 feet apart. They're to be stayed or stabilized by 2 wires attached to a single stake running from ground level to the top of each post. Where should the stake be placed to use the least amount of wire? Again, least amount, so this is asking us to minimize. All right, so let's draw this one. This one might not be as easy to imagine as the other one was. So we've got 2 posts. One's 12 feet high, and then another one is 28 feet high. Well, let me draw this a little bit. So this is 12 feet high, and then 28 would be double that. So just to kind of get the scale here, 28 would be more than double that. So maybe it's like up here is 28. So here's ground level. Again, we're assuming that this is horizontal right here, and they're to be stabilized by 2 wires attached to a single stake running from ground level to the top of each post. So somewhere on the ground between them, and we don't know where. We can't assume that it's the middle, so let me just maybe put it right here. Is that we're going to stabilize these, so it's attaching a wire right here so that this post doesn't move, again, because it says running from ground level to the top of the post. All right, so this is the wire right here, and then we have another wire that's going to go up right here. All right, and we're trying to minimize the amount of wire that we use. Right, so it doesn't make sense to put it in the right in the middle. That would make this wire shorter, but it would make this wire longer. So we're just trying to figure out where is the best spot to place this so we use the least amount of wire. All right, so we know that we want to minimize the wire. So we need an equation that's going to say how much wire we're using. All right, first of all, let's also put on here that this is 30 feet apart. We also should indicate that. All right, so then let's just call this, let's see, the question is where should we place this? So let's call this X right here. That's just the distance from the base of the 12-foot post to wherever we decide we're going to put that single stake in the ground. So then without using a second variable, let's call this part right here 30 minus X. All right. Now, again, we're trying to minimize the wire. And so let's just say W for the amount of wire that we've used. Again, we can't use X because we've already used it here. So let's call this Y maybe, and this Z. All right, so the length of the wire is going to be Y plus Z. And this is what we're trying to minimize right here. So this is our primary. So then we need, again, our next step is we've got to rewrite this so that it's just in terms of a single variable. But as it stands now, if we're looking for how can I rewrite y in terms of z or z in terms of y or something like that, that's not going to be that easy. But if I were to just, let's look at just this part of it. Sorry, I don't know if my fingers are making it hard for you to see that triangle. If I'm relating these 3 right here, I could use Pythagorean theorem and say well, it's possible that I could get y written in terms of x, and then I could do the same thing here. I could get z written in terms of x, and then what we could do is we could write w just in terms of x. So in fact, not just replace one of the variables, but replace both of them with an expression that uses the same variable here. All right, so let's do that. So let's note here that in this triangle that we have x squared plus 12 squared equals y squared, or in other words, x squared plus 144 equals y squared, or we could say y equals the square root of x squared plus 144. Right? We would do the same thing for this one, and we would get 30 minus x squared plus 28 squared equals z squared. This one is a lot less fun. When we multiply this out, we get 900 minus 60x plus x squared plus 28 squared is 784, and that equals z squared. And then when we combine like terms, we end up with x squared minus 60x plus 1684 is z squared. And then when we take the square root of both sides, we end up with z equals the square root of x squared minus 60x plus 1684. Disgusting. All right, and so when we go back up here to w equals y plus z, we're going to write this then as w equals the square root of x squared plus 144 plus, and in place of z, we're going to write the square root of x squared minus 60x plus 1684. All right, so what we've done there is we've said, we're just going to replace the y and the z with an expression of each that contains x. All right? Okay, so we need to find out what the domain of w is. All right, again, the feasible domain here. And so we would say, okay, well, the minimum amount, like, again, silly situation right here, but if we moved the stake right over here, we're thinking about both extremes. So if we put that stake right there, right, then the length of x would be 0, because this would be all the way over here, and x would be 0 and y would be 30. So the smallest amount we could have for x would be 0. Again, dumb, because then this really wouldn't be stabilized, but we could put the stake right at the base of the post. We could also do the opposite. We could put the stake at the base of the other one, right? In which case, the value of x would be 30. Right? So if we put it over here, x is 0, and if we put it over here, x is 30. Again, we're assuming it's going to be someplace in the middle so that x will be between 0 and 30, but we are, in theory, allowed to choose 0 or 30. Right, so again, here we note that this is bounded. So we're going to use the extreme value theorem, right? So that means that we will find the critical numbers of this function, and then in addition to testing them to see what their values are, we're also going to test the two endpoints, so the 0 and the 30. Okay, so then we need to take the derivative, and this is going to be the worst part ever. So the derivative of w with respect to x. And again, here is w. So we're going to take the derivative of that. So we get 1/2 x squared plus 144 to the negative 1/2. And then again, chain rule, so don't forget to take the derivative of inside. And then we do the same thing for this part right here. So we bring the 1/2 down, x squared minus 60x plus 1684 to the negative 1/2. And we need to take the derivative of the inner, so we've got 2x minus 60. Okay, so then because we're going to end up setting this equal to 0, I'm not going to suggest that we do the normal simplifying that we do, which is where we multiply top and bottom by anything that has a negative exponent on it, but now we just put the positive version on it. We're just going to end up with setting this equal to 0, and so we'll be able to move things around with a little bit more flexibility. So what I am going to do is I'm just going to cancel this 2 out with this, so I end up with x over square root of x squared plus 144 plus, and then I'm going to cancel, I'm going to factor a 2 out of this and then cancel it with this. So we're going to end up with, after I factor a 2 out, I'm going to get x minus 30, and then this will flip to the bottom, so I end up with square root of x squared minus 60x plus 1684. And then again, because I'm trying to find the critical numbers here, I'm going to set this equal to 0. All right, so we don't really need that anymore. And now this is what I was saying. We're just going to move this over to the other side. So we end up with x over square root of x squared plus 144 equals, this is going to become negative, so I'm going to write it as 30 minus x over square root of x squared minus 60x plus 1684. All right, we'll cross multiply, and we end up with x times square root of x squared minus 60x plus 1684 equals 30 minus x times the square root of x squared plus 144. And then the easiest thing to do at this point is just square both sides so that we get rid of our radicals. So when we square this side, I'm going to get x squared, and then I'm going to get this outside the radical. So x squared minus 60x plus 1684. And then when I square this side, this one's going to be the easy part. That's just going to be x squared plus 144. And this is going to be 30 minus x squared, which is going to end up giving us 900 minus 60x plus x squared. And then we've got to distribute everything. So we end up with x to the 4th minus 60x to the 3rd plus 1684x squared. Again, the reason that we're doing this is because we're going to combine like terms on both sides. So we end up with, I'm going to do this in the opposite order so that I get these in the right order in the end. So I'm going to get x to the 4th and then minus 60x cubed plus 900x squared. And then when I do that with the 144, I get plus 144x squared. Again, I'm going in the reverse direction here, so I get them in the right order. Minus 60 times 144 is, I think, 8,640. Let me just double check that. That's an x. Sorry, this is so unprofessional here. 144 times 60, yeah. And then I also end up getting 144 times 900, which I have as 129600. All right, so we're going to combine like terms here then. These x to the 4th, I'm going to do a couple things here. First of all, these x to the 4ths will cancel out. And then I only have one x cubed term, and that on each side. All right, so when I bring this, oh no, I'm kidding. Sorry, I'm just thinking here. Negative 60x cubed. Oh yeah, sorry, I only have, this is a squared right here. Sorry, I couldn't tell, it was too small. So these minus 60x cubes will also cancel out. And so we just are going to end up with a quadratic right here. So 900x squared plus 144x squared. And then we've got this 1684x squared. So 900 plus 144. So I get 1044. So I'm going to bring both of those over to the other side. So I'm going to subtract them from 1684. And I get 640x squared. Right, again, I'm combining these two and moving them over, and then I'm going to move everything else over, so it gives me plus 8640x plus, no, minus 129,600 equals 0. Amazingly, they all have a factor of 320. So this is going to be 320 times 2x squared plus 27x minus 405 equals 0. This factors into, in fact, I'm just going to get rid of this 320, so then this factors into x minus 9 times 2x plus 45 equals 0. So that tells us that x equals 9, or x equals negative 45 halves. Again, hopefully you can see that we just need to eliminate this one because we said x could not be less than 0. So we have x equals 9. All right, and then if you remember from the extreme value theorem, which we said we were going to use because it was a bounded interval, that we need to check x equals 9, but then we also need to check our endpoints. And so we're going to set up a table here. Let me just do that on the side here. So we're going to do x and w. Those are our variable and our function. So I'm going to put 0, I'm going to do 9, and I'm going to do 30. And just for time constraint, I'm going to tell you what the values are here. We get approximately 53.04. The actual the actual value, exact value, is 12 plus the square root of 1684. All right, here if I plug in 9, I end up with 15 plus 35, which equals 50. And here, when I plug in 30, I get square root of 1044 plus 28, which is approximately 60.3. Right, so again, we've got 53.04 roughly, we've got 50, we've got 60.3. And so our answer would be, since again, we're trying to use the least amount of wire, we want x to be 9. All right, so where should the stake be placed to use the least amount of wire? We should place the stake 9 feet away from the 12-foot tall post. To minimize the wire. Okay? All right, one more. Okay, so in this one, we've talked about this before, where when we do the domain, you know, what's the interval of values that we can choose from, we said we're going to do the extremes. First, we're going to let x equal 0, then we'll let x as big as we possibly could. And we said it's kind of dumb to do that because sometimes some of the scenarios that we talked about degenerated into weird things. But we did say that it would be possible that the maximum could occur at the endpoint. And so this example is going to look at that. When would we get a maximum at the endpoint? All right, so here we have this example. 4 feet of wire is to be used to form a square and a circle. How much of the wire should be used for the square and how much should be used for the circle to enclose the maximum total area? All right, so we're going to have a circle and we're going to have a square. They don't necessarily need to look like they're about the same size like these are. I just happen to do that. All right, and so we're trying to maximize the area. All right, so the area of the circle would be pi r squared, where r is right here. But again, we're trying to find this part right here because that is the wire that we're using to make that circle. All right, so it's important for us to have 2 pi r also. All right, so this is going to be when we're maximizing, we need this, but when we find the length of the wire, we're going to use that. All right, likewise with the square, and we're going to have to give some other unit of measure here, so let's call these sides x for each of them. So when we do the area of that, we're going to get x squared. But again, we need to find the perimeter here because that's where the wire is, so that's going to be 4x. Okay, so we are trying to maximize the total area. So our formula is going to be something with area. And again, it's going to come from the area of the circle. The circle is going to contribute pi r squared. And the area of the area of the square, which is going to be x squared. So again, this comes from the area of circle. And this is going to be the area of the square. And this is going to be our primary because we're trying to maximize the area. All right. But then we also have this constraint that we have 4 feet of wire to use right here. Right. So that is going to come from, in the circle, that's going to be the circumference, and in the square, it's going to be the perimeter. And so we're going to say that the wire is coming from 2 pi r. Oops, didn't quite look right. 2 pi r plus 4x. And we know that this is 4, right? Because it tells us that we have 4 feet of wire. And again, this is the circumference of the circle. And this is the perimeter of the square. And again, this is our secondary. Right here. Okay, and so we have to somehow get this in terms of a single variable. And I am going to choose to solve for r. All right, so if we want to get r by itself here, then we're going to have to move the 4x over to the other side. All right, so we end up with 2 pi r equals 4 minus 4x. And then we'll divide both sides by 2 pi. All right, so we end up with r equals, let me also cancel this 2 that they have as a common factor. So it's going to be 2 minus 2x over pi is what we're going to then substitute back into our primary. And so we end up with something that's just in terms of x. All right, so when we do that, we end up with a equals pi, and in place of r squared, we're going to fill in 2 minus 2x over pi squared plus x squared. All right, I'm going to multiply this out, and at the same time, I'm going to cancel one of these pi's with the 2 pi's I'll end up getting down here. So I've got area equals pi. In fact, I'm just going to leave that there and then we'll cancel it. So this is going to give me 4 minus 8x plus 4x squared over pi squared. And again, that's where I'm saying that I'm just going to end up with a pi down here plus x squared. And let me rewrite this where I then, I know I'm going to need to find a common denominator here. So let me just multiply this top and bottom by pi. All right, and so then I'm going to end up with, actually, yeah, I'm not going to do that. Sorry, I'm just looking at the little notes I wrote myself here. I'm going to leave that alone. And what I'm going to do is, first of all, I'm going to rewrite this in the correct order. So 4x squared minus 8x plus 4. And then I'm going to divide each term by pi. That'll just make it a little easier when we go to take the derivative. So I'm going to end up with 4 over pi x squared plus the other x squared that we have minus 8 over pi x plus 4 over pi. Okay, and then let me do one other thing. Let me, this was just dumb to do that, sorry. I'm going to combine these two terms and then I'll factor out a pi. I don't know why I did that. So it's going to be 1 over pi, and this will be 4. My goodness, hold on. Yeah. I'm going to factor out a 1 over pi. So it's going to be pi, no, kidding. It's going to be 4 plus, when I factor pi out of here, it's going to be, if I'm going to divide x squared by 1 over pi, it's going to end up giving me pi. And so I end up with 4 plus pi times x squared. That was a horrible description of that. Sorry. Let me just do that one more time, more slowly. Really, what I should have done is exactly what I started to do here. I don't know why I did that. If I just multiply top and bottom by pi so that we get a common denominator here, I'm going to end up with 4x squared plus pi x squared when I combine those two terms right there. All right, and I'm just factoring out that x squared, and I get 4 plus pi x squared. And then we don't need to do that whole breaking it apart, because then I can just factor out that 1 over pi and we'll end up with this. All right, so sorry, that was really horrible. Okay, so then let's go through and say what the domain of this is, right? And so we would say, well, if we come back up here, then again, this, if I used all of the wire for this, again, we're thinking extremes. If I don't make this at all and I use all 4 units of wire for this, then I can only have x be 1, because again, I only have 4 feet. So the highest x could be is 1. And then the lowest x could be would be if I don't make a square at all and I just let it go to the circle, right? In which case x is 0 and all of my wire goes to this. All right, so again, this is our feasible domain where we're just going to say it's just got to be between 0 and 1. 0 is if I use none of it to make the square, and all of it goes to the circle, and 1 is if I use all of it to go to the square, then each side could be 1. All right, so again, we'll note here, domain is bounded. And so we're going to use extreme value theorem again. And so what we're going to have is whatever critical numbers we get from this function right here, to those we also have to add the endpoints right here. All right, as we test them and set up an xy table. All right, so let's find a prime or dA dx. And again, we're going to leave this scalar out front, and so we just end up with the derivative of this term. Again, this is just a really weird looking coefficient. It's just 4 plus pi. And so we're just going to take the derivative of the x squared, which is going to bring the 2 down to the front, and then we'll have that. And then we're going to take the derivative of the 8x and get 8. Derivative of 4 is 0, so we get nothing. And we want to set that equal to 0. All right, so if I multiply this through, well, let's say this. I'm just going to note that I can divide out by a 2, so I get 2 over pi equals, when I take that 2 out, I end up with 4 plus pi, and when I take the 2 out of here, I end up with minus 4. Whoops, I forgot the x. And I want that to equal to 0. I'm going to multiply both sides by pi over 2. So this just ends up giving me 4x plus pi x minus 4 equals 0. I don't really have to do that. I could just bring the 4 over to both sides, or to the other side. Again, I'm not going to do that. Let's save myself the trouble of having to re-explain later. So I'll just move 4 over to the other side, so I get 4 plus pi x equals 4. Divide both sides by 4 plus pi, and I get x equals 4 over 4 plus pi. That is my only critical number. Right, so again, because of the extreme value theorem, we say, well, it's in this bounded region, the max or min could occur on an endpoint, so I have to include those. And so we're going to say, all right, then I'm going to set up a table here with my x values, with my a values. I can use 0, I can use 4 plus 4 4 over 4 plus pi, and I could use 1 as my 3 test values, right? When I find a of 0, right, again, we're back up to the area here, and we're going to use this one right here. When x is 0, so hold on. No, we're going to use this one right here. When x is 0, I get 0 here, and then 0 here, so we just end up with 4 over pi squared times pi. We just end up with 4 over pi, which is about 1.273. When I put 1 in for x, I get 1. I get 1 right here, so 2 minus 2 is 0 over pi, so I just get 0 here and 1 here, so I just end up with 1. This is the really annoying part. Feel free to use your calculator. This is approximately 0.56 right here. So if you plug it into here, you end up with 0.56, approximately 0.56 as your answer. Again, don't trust me on that, although I know it is correct, but feel free to plug it into your calculator. Just plug x in as 0.56 there and as 0.56 there. It'll save you on the algebra part. And so we find out then when we're trying to maximize that actually this right here is the maximum area that we can enclose. In other words, it's saying don't make the square. The biggest area that you can get is if you use all of your wire to go to making the circle, right? And that is true in general, that if you have a fixed perimeter or fixed circumference, that the largest area you can make of any shape, it's not a triangle, it's not a square, it's not a hexagon, always the the circle would maximize the area. So this is the maximum area. And so we're going to say, in order to maximize the area, all of the wire should go to making a circle. None should be used for the square. Okay? All right, that's it. Bye.